Hello, this is Lyutikov, and I would like to discuss coherent emission in pulsars, magnetars, and fast radio bursts. And I will discuss a new model of reconnection-driven free electron laser. And here we see pictures of reconnection on the sun and a laboratory device called free electron laser. And I think in pulsars and fast radio bursts, these two combine, as I will discuss. There are two parts to my talk. First is location of fast radio bursts, and they're clearly magnetospheric events. So first, there were quite a few predictions of radio emission from magnetars and FRBs. First, radio bursts simultaneous with X-rays were predicted in 2002. There are two papers within a couple of days. Narrow band with downward frequency drift were also predicted. Then I was writing that one may expect the frequency drift of the peak of radio emission. And this indeed has been confirmed in case of fast radio bursts. All frequencies drift down. That means it's not a plasma effect, it's a propagation of the emitter within the magnetosphere. Basically, this goes under the name of radius to frequency mapping, and one can show that in case of FRBs, both the rate and the range are consistent with magnetospheric origin. Then there were predictions of a polarization swing within the pulse that was confirmed recently. And those polarization swings are expected to be smaller than for pulsars, because in case of pulsars, our line of sight typically crosses near the magnetic pole. And there was a prediction that radio leads X-rays, and that has been confirmed with the recent observation of this magnetar. And there was also prediction that radio bursts should be seen from unknown magnetars, and of course that has been seen. And the conceptual model that I think in terms of is solar physics of magnetars, that bursts and flares are magnetospheric events, not star quakes. And I think all data are consistent. And just qualitatively, if we compare the solar flare, which shows slow evolution, explosive stage accompanied by different types of radio bursts, ejection of a coronal mass ejection, and they're all seen in magnetars. And again, qualitatively, here is a picture of a solar flare. There is a precursor evolution, impulsive, prompt and gamma ray flares, and a softer tail, and all of these are seen in magnetars, again, qualitatively. And by the way, the difference is that the foot points are driven by electron MHD, in the following sense that the turbulence dies after a few seconds after neutron star bursts. There is relaxation, MHD relaxation at 100 seconds, and then at about 100 seconds the crust freezes. And the point is that the steady MHD state is not a steady electron MHD state. So after crust freezes, electrons start to flow as inertial-less fluid, and they evolve the external magnetic field. So we know X-ray and gamma bursts are clearly magnetospheric events because we see oscillations with known period of a neutron star, and coincidence with radio down to milliseconds argues that radio is magnetospheric too. Then, from the energetics, we can estimate the equipotential magnetic field, meaning the magnetic field that would equal in energy the energy density of radiation, of the coherent radiation. And that equipotential magnetic field estimates to 10 to the 9 Gauss, which is clearly a neutron star magnetosphere. And that's the lower limit on the magnetic field. And also there is this laser intensity parameter A. And if you take it at face value that this laser parameter could be as large as 1,000,000, and that means a particle in the coherent wave oscillates with Lorentz factor of 1,000,000, and that will incur huge radiative losses. The trick is if you have large magnetic field, then instead of large amplitude oscillations with this parameter A, the particle experiences slow drift. So large magnetic fields are required to avoid catastrophic normal losses. And X-ray bursts should originate close in by energy requirement. It will take about about a football field of energy near the surface to produce a regular X-ray burst. And time alignment between radio and X-ray imply that radio is also generated relatively close at smaller than 10 to the 8 centimeters. So, I think all observations are consistent with the magnetospheric origin, and I would like to be contested on that, but I think it's a pretty solid argument. And all predictions, all this predicted and confirmed to a various degree. The mechanism, free electron laser. So it's an old problem, pulsar radio emission, 50 years old, and I think new ideas are needed. And there is a reason why 50 years people are still uncertain. Simple things do not work. Also, probably there is not a single emission mechanism. And what I mean is, if we look at the Crab profiles, there is a precursor, and which looks like a regular pulsar radio emission. And then there is emission from the main pulse and the interpulse, which is probably different from the rest of the pulsar's radio emission in general. And the idea is that this Crab main pulse and interpulse is reconnection driven. And then that connects to magnetars and FRBs. Radio is reconnection driven, not rotationally driven. And fast radio bursts cannot be rotationally driven. They are too powerful, the repeater. The requirement of large spin down energy and no evolution excludes young rotationally powered pulsars. Well, magnetic driven are still okay, and that was I was arguing years ago. Now, the most interesting observation is narrow bands in frequency spectrum, which are seen in Crab and FRBs and on the Sun. And to me, that indicates some kind of a stiff confining structure. And in this case, in the case of Crab and magnetars, is magnetic field. Now, the new model that I'm developing, a free electron laser. And these are laboratory devices where you have a set of magnets and a particle beam is shot. And these particles oscillate, they bunch and produce coherent radio emission. The difference here that we're in a new guide field dominated regime. That needed to be explored in details. And conceptually, the idea is there is Alphian waves that are running around in the magnetosphere, and the reconnection generates a beam of particles that produce lasing in a FAL mode. And in Crab, similar processes occur near the Y point. So bunch is induced by the beam, in the beam by the wiggler emit coherently. And I do fairly detailed analysis of single particle trajectories and with adiabatic switching. Adiabatic switching is important to get correct phases of the particles. And here is the qualitative description of how the emission occurs. Consider a wiggler propagating to the left, an electromagnetic wave to be amplified propagating to the right. And in the beam frame, both have the same frequency. One is boosted up by the Lorentz factor, another boosted down by the Lorentz factor. Then counter-propagating waves give a standing wave charged bunches in the beam frame. And you can write down what could be called a ponderomotive Hamiltonian. Ponderomotive is the interaction of a particle with the waves. And that ponderomotive Hamiltonian has minima, and particles are batched in the minima. And then the wiggler shakes them. and also the phases from different bunches act co-constructively. So each bunch emit coherently, plus addition from different bunches is also constructive. And here is numerical simulations to back up the theory. So top left you see particle trajectories. Here is there's a diabatic switch on region, and you see that bunches are formed. Bunches are 2 bunches per period. And if we plot the phase portrait of the particle, you can even see this formation of bunches by eye. So for example, on on bottom right is velocity versus phase, and I start with homogeneously distributed particles over the phase. The waves come in, and you can even see by eye that the particles are bunched. So the particles are bunched and then shaken by the wiggler. The theory turned out to be really sturdy. As long as velocity spread is less than unity, we are okay. And that was very strange because laboratory FALs are very sensitive to velocity spread. And here guide field dominance helps us, because in a guide field dominated case we have the same trajectory for different energies, while in laboratory plasma, in laboratory wigglers, FALs trajectory depend on energy. And here I draw the phase mismatches between 2 particles with different energies for the usual wiggler and B field dominated. B field dominated is much better, keeps coherence much better. And also mild radiative losses can really narrow rest frame distribution. The frequency, it is independent of the magnetic field, it is independent of plasma density. The frequency emitted is gamma squared times Kc, where K is the basically wavelength of the perturbations, meaning it can work in millisecond pulses, magnetars, and far out and crap, and with different wave numbers, just somewhat different Lorentz factors. And Lorentz factors that are needed are 100 to 1,000, cannot be less demanding. Brightness, temperature, right on. And again, you need a football field of magnetic energy. One of the most interesting thing is if you have a harmonic linearly polarized wiggler, then you expect multiple stripes. And this is indeed matches FRB phenomenology, where if you have narrow emission bands, they always come with linear polarization, what broadband with more wide polarization properties. So the model reproduces correlation of polarization and spectral properties, which is, I think, pretty subtle. Then there is a plasma effects in the beam and the Raman and Compton regime. And basically this does not mess up the phases. And an important qualitative difference between this model and coherent curvature emission by bunches is that these bunches are dynamic. They're not static, so that's why they, it's hard to see how you can create static collection of repulsive charges. Broadband wigglers also create plasma oscillations. For example, here you have 2 Gaussian wigglers propagating to the left. The first creates bunches, the second one shakes them. The model it's highly intermittent because it's explosive growth from noise. And also a subtle point, it's not coherent curvature emission in the wiggler field. The Landau-Miranchuk effects mix up phases. And I also construct a model of light darts. It's cigar-like Alfvén wave packets that are limited both in radial and transverse direction. Radio emission is probably generated in initial stages of the magnetospheric connection, while the magnetosphere is still relatively clean. The giant flare, the rise time of 100 microseconds kind of matches the typical duration of FRB of few milliseconds. And the initial stages of relativistic reconnection can be hyper efficient. Thank you very much.